All right, folks, we're back to another video on permanent magnet synchronous machine control. And today we are going to look at cross-axis decoupling control, another important topic that you're going to see when you work with permanent magnet synchronous machines. Now, you know that we've been studying the permanent magnet synchronous machine for a while. We started looking at it from the rotor reference frame model. And when we looked at the rotor reference frame model, you may or may not have noticed this coupling terms. Okay, and now let's jog our memory back to the three-phase machine that we had. Okay, if you recall the three-phase machine, I'll just draw inductances. We do have resistance and back EMF. Okay, now in the machine, when they are wound, we do see coupling between these windings, right? Why do we see that? If you look at the stator, there are windings that are placed on the same stator. Okay, so when flux is generated, they will link through other windings. Therefore, we'll have some coupling involved with the inductances. Okay, so it's a little bit messy if you go back and look at those what stator reference frame voltage equations. The inductance matrix is a 3x3 matrix, which is heavily coupled. And very difficult to understand, right? However, when we do the rotor reference frame transformation, we can see that there is some coupling between the two equations. So essentially what we mean by here is, if you think of this voltage equation, this is a Q variable, QSR, right? This is another Q variable. This is our speed. Everything here is Q except for this term and this term, right? This is a back EMF term, and then this is another back EMF term because of the flux linked by the d-axis. Okay, and vice versa. If you look at this equation, there is a d-axis voltage, d-axis current, and q-axis current. So there is another coupling term here. Okay, now it's not as complex as the stator frame model. However, we do have some coupling between the two axes, the q-axis and the d-axis. Okay, so we call them the cross-axis coupling. Cross-axis coupling. Okay, so what? So we have some coupling between the two voltage equations. So what? Okay, so the problem with this cross-axis coupling is, let's say you have a current regulator to regulate q-axis current and the d-axis current. Okay, now we know that q-axis current for a non-salient motor, it directly controls torque, right? And then d-axis current is used to control the flux if you want to do field weakening control, right? Now, let's say we apply a step input or step change into the q-axis. So we are changing the reference. Okay, when we do that, that reference will influence what? It's going to influence my d-axis. So that means in a change that's only occurring or that was requested on the q-axis, it's going to make the d-axis work, and then the regulators will have to work and try to regulate the d-axis voltage as well as q-axis voltage. Okay, so this is a little bit undesirable. This creates, because of the coupling, we might not be able to handle very high dynamics. So engineers have thought, okay, can we come up with a strategy to remove this coupling from the two equations? That way we can independently control q and d axis without having the coupling terms. Okay, so that way, if you change your Q axis, if you apply a step preference or step change to your Q axis, it's not going to influence your D axis. And if you change, or if you apply a D axis change, it's not going to influence your Q axis. Okay, so that was the goal. And I recommend you to, maybe pause the video at this point and think how you can achieve this. Try to contemplate, if you can come up with an idea. But I will go ahead and go to the method that we can use to achieve this. Okay. All right. So this is how we do the decoupling. Okay. You've seen this before. We have gone through this field-oriented control strategy with just the current loops. Okay. In the regular setup, we only have this PI regulator, right? We have the current measurements coming in. So we have, this is the motor. We have our inverter and the space vector modulation scheme. We have the 3 current measurements. We don't need speed measurements in the regular case, unless you are doing speed control. And then we have a position measurement. Position measurement, of course, goes to our reference frame transformations and the voltage generation. Okay, so we have our PI regulators, and it's happy, it's generating current. However, if there's a reference change in the D axis, that will affect our Q axis from, because the motor has these equations, right? Inside the motor are these equations. So they're going to get influenced, and therefore the actual currents along the Q axis will change, even though we held the reference constant. And in that case, the PI regulator will try to bring it back, and in doing so, it will change the Q axis voltage. Okay, so, but with this coupling term, what it will do is it will look at what the currents are on the Q and D as they are being changed, and it will introduce the term beforehand. It's a little bit like feed forward control. You're looking at what the Q and D currents are doing, and rather than letting the regulators take the burden of correcting it, we correct it ahead of time, and that way it doesn't propagate through the feedback loop and tell the controller, hey, your current is low, try to correct it. Okay, so with this we can now decouple the influences between the Q and the D axes. Okay, and we can also use the back EMF as a decoupling term if you want to. Let's say you have a speed variation going on, and you prefer not to have that speed variation influence your current loop. So you can use this kind of a method to compensate for such a method. This way, if the speed is increasing, you're basically adding more voltage without changing the regulators to influence that. You're basically increasing the voltage or decreasing to accommodate that change in speed. Okay, so that way the gain will not be on the regulators. All right, so this is the basic decoupling approach, useful for high dynamic applications, and I'm sure you've seen people talk about it. There are, in certain applications, this is advantageous, and in certain applications, they may not. So you have to pick and choose what you use it for. And then the other aspect here is we do need to have very good or decent enough parameters of the machine to be able to do this. Okay, so if there is temperature variation, so we need to be able to handle that variation, somehow correct it, as long as the variation is not small. And then we do have to have speed measurement in our system to be able to update the voltages as the speeds, the electrical frequencies change. Okay, so This is I know this is the shortest video, so this is basically the idea behind decoupling control. Let me know your thoughts, ideas, and we can I hope to see you in another video. Okay, thank you.